Right, so my name is Tomas. As was mentioned, I work for Second Quadrant as a database engineer. And the topic of my talk is actually performance improvements in 9.5, 9.6, and beyond. Like a look out into the future of what kind of performance improvements you can expect. So there's a version of these slides, like a slightly older version on SlideShare. I will upload the version that I'm using right now after the talk. But most of the slides should be the same, right? It's a talk that I've given on a few conferences before. Obviously, it's updated. It's new data, new results, and so on. Anyway, so what are we going to talk about? If you look at each Postgres version, there is a lot of improvements. And if you've been to the talk given by Magnus before lunch, you probably have a good idea of which kind of improvements are in 9.6, which is probably going to be released maybe in the next few weeks or maybe days. And many of those improvements are actually related to performance. So they are either improving performance kind of implicitly. So if you are using Postgres, you will benefit from them, or it's an improvement that you need to enable somehow. In any case, if you want to just see a list of improvements in each Postgres version, you can use release notes, right? But it's kind of superficial, just a list. It doesn't really give you any good sense of impact. Like, is it going to improve the performance by 10% or 100%, or is it going to be like a million times faster? That's difficult to judge based on the release notes. And there are many talks about the features and improvements in general, like covering all the changes in each Postgres version. And this talk is limited just to the performance improvements that somehow affect how fast the database is actually processing data. So what are we going to look at? We will look at 9.5, 9.6, which 9.5 is the current stable version. 9.6 is the next stable version that should be released soon. Maybe if I have a bit of time at the end, I will talk about which improvements are either already submitted for 10.0 or that I expect to be submitted for some next version of Postgres. If you look at the release notes, like there's a lot of different improvements related to performance. We will look at the main improvements, the most significant ones, and we will look at the complete feature. Sometimes the commits or the features are spread across multiple commits. We will only look at the total feature. I'm not going to look at features in any particular order, like most significant ones or most important ones or something like that. It's simply mostly logically ordered so that it makes sense. And the main difference compared to the other talks is that I will try to showcase the impact of the performance improvements. Because Magnus talked about all the changes, all the improvements. He had very little time for each feature, so he didn't actually have a time to show the impact of that. So I will try to do that, and that's the point of this talk. But nevertheless, there are dozens of additional improvements in each version, and I simply don't have a time to deal with all of them. So maybe, in any case, look at the release notes. Maybe there's something interesting for your particular use case. So, by the way, if you have any questions during the talk, just raise your hand. I will try to answer the question immediately. If it's a more complicated question, maybe I will leave it at the end of the talk, but don't wait until the end of the talk. Right, so the first, let's look at the Postgres 9.5 and the improvements in that. You might already be using 9.5 in production. I hope you are not using 9.6 in production yet, yeah. So 9.5 is one of the versions which has a significant improvements in sorting, performance. And you might actually say that you don't really care about sorting, right? But the database is actually using sorting a lot internally. So for example, when you do create index or cluster or something like that, the database is likely doing a huge sort internally. Of course, if you are using queries with order by clauses, it either has to use an index to do that, or it's actually doing an explicit sort, right? So there's a lot of places doing that. And there are two improvements. One thing is Postgres internally uses SQL callable functions to do the sort. And in 9.5, actually, this need was eliminated in many cases. So we can actually remove a lot of overhead and call the functions, the comparison, do the comparison directly. So that's really interesting. The more significant or more invasive change was actually using something we call abbreviated keys. And if you are using libc or some other library implementing POSIX, there is something called strxfrm, which means reduce the long value into much shorter key, and by comparing the key, you should get the same ordering. So this was implemented by Peter Geoghegan, and it was implemented in 9.5 for a subset of data types, varchar, text, numeric. It wasn't implemented for char values, but that was added in 9.6, as we will see. And this is a significant improvement because, because it allows you to actually use memory much more efficiently, right? Because those short keys, the abbreviated keys, are shorter. That results in better cache usage, and the result is quite dramatic improvement. And this is actually the first showcase of the performance improvements. First, I will generate two tables with 50 million rows each. The first table is not sorted at all, right? It's random order, random data. The second table is already completely pre-sorted. Why I am doing this? The sort algorithms behave differently for when the data is randomly sorted or not sorted at all, and when it's perfectly pre-sorted. And you could think about some other cases, like when the data is sorted in the opposite order and so on. And then you can run a query, which is actually sorting the data, right? So in the first case, it actually needs to do a sort. In the second case, the data is pre-sorted, so the algorithm should be maybe smart about that. And we will, of course, measure duration of the second of the query, right? So that's the benchmark. And the result looks like this, right? This is a duration, so lower values are better. The blue bars are 9.4, and the red bars or orange bars are 9.5. And you can see that there is a quite significant and dramatic improvement, like 4 times faster sort in 9.5. There are a few other, data sets. The random ordering, random sorted input is the last one. Then there are already sorted data, data sorted in the opposite direction, data that is almost sorted in the opposite direction, and the random data. And you can see that first we have a significant improvement in 9.5, but it's also much more consistent across the data sets. While 9.4 jumps a bit up and down, 9.5 actually is almost exactly the same, except for the last case, right? So that's, I think, a significant improvement. And this is important because if you are doing, for example, large aggregations on large data sets, right? You are using group by, then we can't actually do that using hash table, right? Because that wouldn't fit into memory, probably. But we can actually do that using sorting, and sorting is really a key performance improvement here. So that's quite significant. If you are using like analytics, this is going to help you a lot. Okay, any questions about the sorts? Yeah?
So you mentioned how it influences group by. Is that implemented internally? Like, would that?
Well, there are multiple, I think there are two different implementations of group by. One is hash aggregate, right? But if it doesn't fit into memory, the hash table, you need to do a group aggregate, which means that requires a pre-sorted input. So there, if you do explain plan, explain of the query, you will see that there is an explicit sort before that, right? Okay, so the next step or next thing is hash joins. Again, we have managed to reduce the overhead with memory allocation, which is a problem we have for a long time. But the other thing is, if you are familiar with hash tables, what we use for hash aggregation is a set of buckets, and each bucket contains a linked list of entries in the hash table, right? And by default, it used to be, the hash table used to be sized for 10 tuples or 10 groups per bucket. And whenever you look for, you need to add another tuple into the hash table, you look up the group in the hash table, the bucket, and then walk the list, which is fairly fast as long as the lists are fairly short. And by default, it was set to 10. So we ended up with like 10 groups per bucket. And it turns out it's actually a significant performance problem because first, we need to walk the list. Maybe we don't. Maybe we can size the hash table differently. And the second thing is, if there happens to be an underestimate, right? If you only expect 10,000 groups, but you get 10 million groups, you end up with very long lists in the hash table. And so what we have done in 9.5 is we have changed the sizing of the hash table to actually use a single entry in each bucket. And we have also enabled dynamically resizing the hash table based on actually the input data, right? So we are not limited by the initial estimate, but when running the query, we can actually resize the table based on the input data and how many groups we actually get in production. So again, a simple example. So we have a join with two simple tables. You could see this as a fact table with a small dimension. When the dimension gets to be hashed into the hash table, and then we walk to the large table with 50 million rows, and we join the two tables, right? And we will measure how long this join takes. Right. So we keep the fact table 50 million rows. We change the size of the dimension table to kind of see how that behaves at different sizes of hash tables. And again, the blue line is the duration on 9.4. So you can see it takes like 40 seconds. It kind of jumps depending on how accurate the estimate was or how exactly was the hash table sized. But on 9.5, which is the n tuple per bucket, the size of the linked lists in each bucket with 1, you can see it's much faster. It's like half the duration, right? It's twice as fast. And obviously, this is for the case when the estimate was pretty accurate, right? When the hash table was sized as expected. But if you get an underestimate when planning the query, you can get like a significantly longer durations on 9.4, while 9.5 is going to handle that just fine. So this is one of the patches that actually I wrote. And just to give you an example of how long, actually, how significant the improvement is, I started to investigate a query which was taking like half an hour. And after deploying this fix, it takes less than half a minute, right? So it's like a huge improvement. And you could even say that the hash joins were broken before that, right? I mean, you will still get the correct results, but it wasn't really a nice behavior, right? So any questions about the hash joins? OK, so next thing. This is actually, if you know about Postgres, like what are the strengths and great things on Postgres, I think one of the greatest features is extensibility, right? So you can actually implement reasonably, in a reasonably simple way, new index types, new index schemes, and so on. And BRIN indexes are an example of that. The usual indexes actually track individual tuples, right? So you get a tuple which is stored in the index, and then you can look up the tuple using a value. BRIN indexes are very different from that. They don't actually track individual tuples. They track a summary of tuples on a page or on a range of pages. So instead of having a record or entry for each tuple, you will have, for example, a minimum and maximum value in a column on a page, which allows you to do pretty good optimization during execution, right? So when you then look for example, tuples between where the value in the column is between 100 and 200, you can simply look through the summary of pages, and you will immediately know which pages probably contain tuples with the values, right? It doesn't allow you to do regular index scans. It only allows to do bitmap index scans. But that has another benefit. It's actually a sequential scan, right? I mean, sequential approach or access to the table, while regular indexes generate a lot of random I/O when accessing the table. So I heard that this is actually called by some people auto-partitioning. It's very efficient for certain use cases when the indexed column is kind of correlated with the table, like a timestamp in a log table or something. And to show you an example of that, I will create a simple table which contains like 100,000 different values, but those values are kind of strongly correlated with the table, right? It's 0, 1, 2, 3, up to 100,000, and then again repeated over and over. And if you create a B3 index and a BRIN index on that, you can actually see what's the difference in performance, right? And then you can do a query like this, which, depending on the value, selects a random fraction or a different fraction of the table, right? So if you have 100,000 values there, if you use the query with value lower than 1,000, it should give you like 1% of the table and so on. And we can then compare the performance of the B3 index and the BRIN index depending on the fraction of the table returned from the query, right? And this is like a comparison of these plans, where the blue line is a sequential scan, right? You simply scan blue line is a B tree, which is kind of linear, right? It's linear because the table is perfectly correlated with the index most of the time. The yellow line is a BRIN, which only keeps a summary for 4 pages at a time. And each page is like 8 kilobytes, so this is like 32 kilobytes of data. And you can see it's like from the beginning, it's faster than a B tree. And if you use the default BRIN configuration, which is using 128 pages, which is like 1 megabyte of data, you can see that it has a higher startup cost. Like it needs to scan at least 4 megabytes of data every time, but then it actually starts beating the B tree index once you scan more than like 50% of the table or something like that. So it seems quite nice. If you used a different, different type of data set, which is not as correlated as this one, you would probably get a slightly worse performance from both the B tree and BRIN indexes. But you need really to consider that when creating the index, right? And the main benefit of BRIN indexes is the size, right? So in this example that I have used, the B tree index, the default tree-like index, is like 2 gigabytes of data. And the BRIN index in the default configuration is like 130 kilobytes. Like it's like less than 1% of the B tree index, which allows you to keep more indexes in memory. It actually improved the performance quite significantly. And you can, of course, create a the BRIN indexes much more fine-grained with, for example, up to just a single page precision. In that case, it's like 11 megabytes. It's still a fraction of the B tree. Well, any questions about the BRIN indexes? Of course, minimum and maximum are not the only type of a summary we can keep in BRIN index. There are patches, there are plugins, contrib modules that provide, for example, bloom filters, right? So instead of tracking min-max, you can actually have a bloom index, bloom filter, or when you are dealing with, for example, geometrical data like points, you can also have a summary which is like a rectangle in the multidimensional space. So there is a lot of interesting things happening here. Okay, there are many, many other index improvements in 9.5. So for example, we are reducing the overhead with just copying data in memory for no particular user reason. We can also do index-only scans with additional data types in GIST. And in some cases, the bitmap index scan was spending like half of the time in building the bitmap, which wasn't really necessary. So I think Oleg or Theodor improved that, and you get actually like twice as fast bitmap index scan in some cases. So that's really nice. Another thing that you can see over the last few releases is actually improving behavior of Postgres on large machines, right? So if you have many cores, a lot of memory, and so on, we try to actually improve the behavior of Postgres by reducing overhead with associated with maintenance of share buffers, different types of logs, reducing log strength, and so on. So this is a significant improvement in that area as well. The first release that actually improved that quite a bit was 9.2, when we got like in some workloads like a linear scalability up to 64 clients or something like that. And we only claim 64 clients because we didn't have a larger machine at the time, right? So that's it. Postgres also includes something we call data checksums, which protect the data files from data corruption due to, for example, broken disks or something. Up to 9.5, we've been using software. Yeah.
The CRC stuff is actually not for the data files; it's only for the write header.
Really?
Yes.
Okay. Are you sure about that?
Also, something very good, very expensive.
Okay. Yeah. Okay. So, but anyway, we've been using CRC which was implemented in the software, and in 9.5 we have switched to optimized instructions that are built into CPU if available. And if not available, we have switched to an optimized algorithm. I think it's sliced by 8 or something like that, right? Which effectively, if it was, for example, 10% overhead before, it's like less than 1% now, right? So significant improvement in terms of throughput. And of course, there is a lot of improvements in the planner. We are constantly making the planner faster, smarter, able to optimize queries better, and so on. Right. I think this is the read-only scalability in 9.5 compared to 9.4. You can see that it's effectively without any drop down after 40 clients in this case, right? Yeah. Right, so that was 9.5, the current stable version. Now, what you can expect from the next stable version, which will be released soon. So the first major feature, a major improvement in their version is parallel query. So Postgres was initially limited by a single CPU per query. That works quite fine when you have very few CPUs in the machine, because you are probably going to saturate or use the CPUs anyway. And it's perfectly fine for OLTP workloads, right? Where the queries are fairly simple, so you wouldn't get a lot from the parallel behavior, but and you kind of expect to run multiple queries at the same time. But people have been using Postgres for like data warehouses, and as we get faster or more powerful machines with more cores, that tends to be annoying because you have like 4 CPUs running at 100% and then 30 CPUs doing essentially nothing because we can't use them, right? So 9.6 should actually be a first step in being able to use more resources available on the machine. It's difficult to say that it's a complete solution because we can only parallelize a subset of the operations in so far. So we can parallelize sequential scan, we can parallelize aggregations, we do have implementation of nested loop and hash joins that can be parallel. We can't really parallelize queries that do any sorts of updates or inserts or anything like that. So read-only queries at this point. And it's only really efficient on large tables, right? So if you have tables that are like less than a gigabyte, you probably won't see a lot of improvement there. In the future, I think there is already a work in progress for 10.0 to, for example, parallelize create index, maintenance operations like vacuum, and so on. I'm pretty sure that Peter Gigan, our sorting guru, is working on a parallel sort and some other stuff, of course. Right. So let's showcase this a bit. So I will create a simple table, a single table with, I think, like 100 million rows. I can't really read the zeros from here, but I think it's 100 million rows. And I will simply aggregate the data, right? It's a simple analytic query on large amounts of data. The table, I think, ended up like 8 gigabytes of data. And on 9.5 or even 9.6 without enabled parallel query, you will get a plan like this, right? It's a simple sequential scan. OK, so this is a wrong plan, I think. Yeah, I think there should be a join. Yeah, it's actually a join to the dimension table, right? So it's doing a join and aggregation on that. And this is a plan that you will get on 9.5 or even 9.6 without enabled parallel query. It will simply do a sequential scan. In this case, the database decided to do a hash join, and then it will aggregate the data. It doesn't need to do any like hash aggregate or group aggregate because there is no group by clause. So it will simply produce a single number, right? And once you enable the parallel query, which in this case is done by setting max parallel workers per gather, I've been really, really, lazy, so I just set that to 32, which is fairly high. But the database decided to use partial aggregate, which is a parallel aggregation, and it also decided to then do finalize aggregate, which collects the data, the pre-aggregated data from the worker processes, and produces the final result, right? You can also see that it decided to use 9 workers. I mean, there is workers planned set to 9. It depends really on the size of the table up to the database, right? And how this actually, well, if you run top on the machine, you will see something like this. So there is one process, which is the backend process running the query, and multiple independent processes attached to that, which are the worker processes. And you can see that from the top output. It's fairly clear. So in this case, it ended up using 9 processes. And the first bar is no parallelism at all, right? It's still like the old way of running queries. It took like, I think, 6 minutes, right? It's like 360 seconds. And with the 9 workers, it was almost exactly 9 times faster, which is fairly nice. Of course, in real queries, there will be slightly slower improvement depending on how much on the amount of communication between the different processes. Right. If you want to know more about the parallel query, there is a very nice talk by Robert Haas available on YouTube. I think it was from this year's PGCon in Ottawa. And he's one of the guys who, like the lead developer of the feature, if that's appropriate term. And he has a really deep dive into the feature, explaining how is it exactly implemented and so on. So I would recommend that if you are interested in details.
There were questions here.
Yeah?
Is there any way to enforce like this many workers I should use in this?
No, I think you effectively set a hint for the planner, like you can use up to this number, and the database, based on some costing or optimization, will decide how many workers to use. And it's based on size of the table, how many workers are available in total, and some other things. In my experience, it's like one worker per gigabyte or something like that, but it's probably much more complicated. I'm not really sure.
Or is there any parameter I can change to enforce it to use more workers?
Well, you could mess with cost variables. I mean, like,
Random base,
I mean, there are cost variables for parallel mode, which say, for example, how expensive it is to set up a parallel query. And if you set that to 0, you will say it's for free, right? But I'm not really sure how to enforce a particular number of workers. Yeah. Okay, so thanks for telling me, because I don't really see anything because of the light. Yeah, so the next feature is aggregate functions. There's fairly annoying behavior in the old versions of Postgres. So if you do, for example, multiple aggregate functions like sum, average, and so on, they internally use the same state, right? So they keep the same type of information, and each of them has to update that independently, which means that's a lot of computation in some cases. So 9.6 actually is able to identify those cases and say, well, I don't really need to compute those states, those aggregate functions independently. I will only do the final, computation of the from the intermediate results to the final result differently for them. Which means we don't need to use memory, we don't need to use CPU cycles, and so on. And to show you that, I will use a simple table again, generated with 50 million rows. And instead of a single aggregate function, I will use 2 aggregate functions that actually can share the internal state, right? Because sum will keep the total, the average needs to keep the total and the count, right? That's how the functions work. And this is the improvement. Like, I mean, before it's 9.5, the red one is 9.6, and it depends. I mean, the effect depends on the data type, because if you work with big integers, the 64-bit integers, that's very fast, but numeric, doing computations on numeric is much more expensive. So if you actually reduce the amount of computations with numeric, it's much more significant than with big integers. And you can see that on the big integers, we have saved like 20% of the duration, while with numeric, we have saved like 30%, right? So, and this is, of course, something you don't really need to, you will get this benefit even if you don't change the queries at all. I mean, that's like implicit. It will simply be faster out of the box. Right. And now for something completely different. Checkpoints. Is there anyone who didn't have a performance issue with the checkpoint? Right. So a checkpoint is a process when we kind of synchronize memory, the shared buffers, with disk, right? We need to make sure that all the data that were changed and written to transaction log and modified only in shared buffers are flushed to disk, and we can actually get rid of all parts of the transaction log. By default, it happens every 5 minutes. You can increase that, and you should increase that possibly up to 1 hour, which is the current maximum value. And but still, even if you do a checkpoint with, for example, 100 gigabytes of shared buffers every hour, it's still significant. The problem is we actually write the data only to the kernel, right? We don't write the data to the disk directly. We hand it to the kernel, and the kernel sometimes does funky stuff with that, which sadly results in like fluctuating or spikes in latencies, performance issues, and so We don't really want to abandon the file system idea and the page cache idea immediately. So instead, what we decided, or what Andres implemented, is playing nice with the kernel. Instead of writing data in some random order and leaving all the optimization up to the operating system, what we do is we try to write the data in like a sequential manner. So we first sort the data before writing it to the operating system. Hopefully, the operating system will be happier with that, and the disk's storage will handle that more nicely. And second thing, we don't really let the kernel, the page cache, to accumulate large amounts of dirty data, which results in like the latency spikes. But we do a flush fsync on the data files once in a while, which means that the kernel will write the data in smaller chunks, and it's going to be more sequential. And I don't have any charts for that, so I have simply stolen slides from a few slides from Andres. If you want to see a complete, complete talk from FOSDEM, there is a link down there. I will just show you 2 charts that demonstrate the impact, right? I think this is a really bad behavior, like an example of something you don't really want to see on your production, right? This is a PG bench with 32 clients. You can see that after the first 5 minutes, which is the default checkpoint timeout, the database started to do a checkpoint, which results in like huge changes in transactions per second. And that's the blue line. You can see that from like 1,800 transactions, it drops to like 400 or even below that, and then gets back and down and up and down, and so on. That's not something I would say is a good behavior. And you can also see that the latency spikes from essentially 0 to like 100 milliseconds or something like that. Again, not really nice behavior. So after the change, you will get something like this. I mean, it's not exactly the same time scale, but you can see that after like 5 minutes, the checkpoints start to happening again, but there are no, the behavior is much less dramatic, right? There is a drop in performance to like 1,200 transactions per second or something like that, but the latency is almost unaffected, and I think that's very nice improvement. Of course, this depends on how exactly is your kernel configured. It depends on the storage. It probably wouldn't be a big issue on like flash storage, but it's definitely an issue on rotational devices. Right.
It's worse on flash.
It's worse on flash.
On lots of flash devices, because the write amplification on the flash makes it really bad, the random writes. Because
Okay.
they write, like for every 8 kilobyte write, they write like 64 kilobytes. That makes it really bad.
Okay.
Especially on the lifetime, how long your
Okay. Well, I've done some tests on the flash I do have access to, and it seemed to behave like fine. But there are many flash devices with different behaviors. It's really difficult to say that for sure. So okay.
Question.
Yeah.
You said OS training. What's the no dirty?
That's basically setting dirty background ratio to, or dirty background bytes, I think, to 16 megabytes or something.
Oh, it's really tiny.
Yes.
Got it.
I mean, that is not necessarily something you want to do actually.
Yeah.
I mean, the graph you copied here is not the one from the actual improvement.
Yeah.
But the one is where I did this work manually in the kernel by setting the config, changing the config
Okay.
settings, but it looks pretty similar.
Yeah. Okay. So I have copied the wrong slide, but that's another reason why actually you should check his talk, right?
It's also enabled by default.
Yeah. Okay.
Disable as you wrote.
Yeah. that's all about checkpoints. 9.6 also includes a lot of improvements about sorts, again, from Peter Geoghegan. It extends the abbreviated keys improvements to other data types, so it actually works with UID, binary data, and so on. It allows this behavior or this improvement for ordered set aggregates, right? Which is a special type of aggregates. If you haven't heard about that, you don't need that. There are a few other improvements here. I'm going to skip about that. One thing you should know about the abbreviated keys is that it's sadly disabled for a number of locales because the libc implementation of the locales is broken. But we are looking into finding a workaround for that. It will be still usable for like UID or data that are not associated with locales, and eventually we will enable that for locales again. Okay, this is the impact of improvements in sort on 9.5. Between 9.5 and 9.6. You can see that for small work memory settings, it's pretty much the same. For larger or medium work mem settings, we actually improved that by another 10% or something like that, simply by using a different algorithm, which is more cache friendly with respect to the caches on the CPU. And I'm pretty sure Peter Geoghegan has a few things in his sleeve regarding sorts, so at least based on his posts to hackers, I wouldn't be surprised if we get like another 10 to 20% improvement in 10.0. Freezing. There's a thing, we have only 32-bit transaction IDs stored in the data files. So once in a while, we run out of transaction IDs. It used not to be an issue because we simply didn't have a hardware capable of doing that many transactions. Nowadays, we can do tens of thousands of transactions that actually write data per second, and you can run out of transaction IDs within a few hours, right? And in that case, we need to do something we call vacuum freeze, which effectively makes sure we don't lose a track of what is the past, what is the future in the transaction log. And up to 9.6, that essentially meant we have to scan all the data files, right? So even if you have a huge multi-terabyte database, which only actually modifies the last few % of the data, we had to scan everything from scratch. And 9.6 introduces something we call a freeze map, which allows us to skip the sections of the data that were not actually modified since the last vacuum freeze. This is a single most important change, I think, in 9.6 for DBAs, right? Because what tends to happen is that you are running a database in production, and one day it's going, the performance drops to like 10% of that, and soon after that, it actually shut down automatically to prevent any data corruption. And that's usually how people learn about vacuum freeze, and then have to set up monitoring and so on. So vacuum freeze, the freeze map is an improvement of that. Right, and I have a slide about a few changes in the future. So if you have been at the first keynote today, Simon mentioned Uber, right? I'm not sure if that's the right pronunciation here, but we know the company. The worm is one of the improvements that are implemented as a result of their feedback, right? So they complained about not being able to do hot updates, about write amplifications and so on due to indexes. And the problem is that if you update a column which is indexed, you need to update all indexes, right? Even if those other indexes don't really deal with the column at all, which means you need to write all the changes for all indexes into transaction log, and that is something we call bright amplification. And Worm says, well, we don't really need to modify all indexes. We will only modify indexes that that actually use the column, right? That the other indexes will not need to be updated. On the next slide, I will show you an example, a chart with the impact of that. There's also a few other patches. There are also a few other patches improving index only scans for expressions and so on. As I mentioned, Peter is already working on parallel and partial sort. I'm sure there are other people working on that as well. There are other parallel query improvements, like being able to parallelize additional operations, execution nodes, and so on. There's a patch that implements declarative partitioning, because the partitioning we have in Postgres is kind of a misuse of unrelated feature that kind of works, but not really. And declarative partitioning would be a really nice feature because it would allow optimization or significantly smarter execution of queries on that. There are also a few people working on features from columnar databases like vectorization, compression, and so on. There are a few improvements in the planner again, like being able to plan queries that reference correlated columns. And there is also a thing, a patch proposing different types of temporary tables that don't actually cause issues with catalogs. So I think this is really a brief outlook into the future. Maybe not features available in 10.0, but definitely features that people work on and are interested in. And just to show you as a last slide, an impact of the worm is, this is a simple PG bench test. The number is like transactions per second, right? So the higher, the better. If you use the default table fill factor, then on master, you will get like 1,100 transactions per second. With the worm patch applied, without any changes to the queries or anything, you will get like a 75% increase in transaction rate on the table. And if you actually decrease the fill factor to keep a bit of free space on each page, you will get actually like 1,300 transactions on master. And with the patch, you will get more than 100% improvement in transaction rate. So that is actually the last slide I do have, so I will leave it here. If you have any questions about any of that, I don't think we have time for that right now, but I will be around, so you can ask me about whatever you want, right? So thank you for being at my talk. Hopefully it was useful for you. I don't know. And